today's topic is the sanity checks. Okay, sanity checks. Let me very timing check. Okay, so sanity checks, like, okay, we are good, like we are good with all the inputs. We know we got the inputs, and then next our step is like we need to sanitize the quality of the inputs. So that is we call it sanity checks. Like, let's say like sanity check nothing but it ensure the correctness or quality of the inputs. Okay, let's say you buy one product, uh, like you buy product from the market. So before you use it, you will check, right, like there is any defect or malfunctioning or not, like any if it is any defect or malfunctioning is there or not, right? So it's the same way, that is called also sanity checks. Before you buy, you will check all this. Here in our physical design flow also, like very similar to that. So before we consume or take the inputs from others, like you get the inputs from different teams. So you need to ensure that all the inputs are correct, or the quality is good or not. Okay, that's the reason we perform the sanity checks. Okay, so basically in the sanity checks we perform three types of checks. One is netlist check, and the timing check, and also the library check. Yeah. So only three types of checks we perform in the sanity checks. Okay, this is an interview question, guys. Please understand this. The interviewer may ask you like, what are the sanity checks you do before you start the PD flow? So you should be able to tell the definition of the sanity checks. Like, it is the sanity checks. It ensures the correctness and quality of the inputs, and it checks the netlist check and library check and timing check. Okay, let's see library check. Okay, let's go with the library check. Okay, what are all the sanity checks? First, library check. Okay, then netlist check, check, and the timing check. Okay, let's see what is the library check. Okay. Okay, so the library check, basically it is two types. One is logical library and the physical library. Logical library and physical library. Okay, two types. Okay, so in logical library, it contains the timing, power, noise of the logic information of the cells. Okay, what it contains, the logical, it contains the timing information and the power information and the noise of the each cell. Okay, and the physical information, physical library, sorry, physical. Okay, physical, it contains the real layout topology of the cells. Okay, real layout topology of the cells. So in the library check, it check, basically these are two types, logical and physical libraries. In the logical library, it checks the it contains the timing and power noise of the each cell. And the physical library, it is the real layout topology of the cells, like how much is the cell height. Let's say, so this is your maybe buffer, let's say. Okay, this is your buffer. I told you, right? Like in the real layout, like everything will be square boxes. Okay, like this. So the logical means this one. It's a logical. What like what exactly what is the logic? And in the physical view, like how much the height? Okay, height. This is h. Okay, how much height and width, w. So how much height, width. We also call this as a footprint. Okay, you remember this word? Okay, footprint. Generally in real time we say like what is the footprint of the cell. Footprint is nothing but the width and the height of the cells. So that kind of this kind of information will be available in the in the library library check. Okay, so okay, we know like okay, library check will contain this kind of information, but how do we verify in our actual design? So there will be some commands like check library underscore library, or else check design. There is one more command also, check design. So later I will show you in our lab sessions like these commands how it works, and it dump basically this command will dump the report. In that report you need to study any logical details are missing or physical details of missing of the cells. We need to study that later. Okay, this is very important. If it is missing, right, you don't see this physical view in your layout. Okay, if they don't give this information, you don't see this physical view in the layout. Okay, then you cannot use it. If you don't have the buffer, then how do you optimize it? You cannot optimize it. So you should identify this issue. Okay, so there will be a command, there will be a commands like check design also, like it is innovus. Okay, the cadence tools. Okay, check design. In cadence tools like no underscore, but in the synapses tools everything will be underscore like this. Okay, check design. If you want to check the timing library or physical library, maybe you put the physical library here. There will be some options available, physical library like this, and or also maybe some logical library dash logical library. I'll show you this. These are just commands. Okay, maybe you may be asked like what are the commands you use to check the library check. So then you need to tell, if you tell at least some check library or check design, if you tell these commands also go enough. Okay, and there is a command also, check design dash all. So it checks both like a logical and physical also or at once. You don't need to specify which check you wanted to check. So you don't need to specify dash all, does all the checks. Okay, and next let's see the netlist check. Okay, if you don't understand anything, please let me know. Okay, netlist check. Okay, so netlist check, it basically check the output should not be tied to the ground. Okay, one point is like output. I'll tell you what exactly what does it mean. Output shouldn't be tied to ground. Okay, let's see. So okay, so let's see. This is your cell. Okay, maybe some inverter. Okay, this is CMOS diagrams, right? I think you guys already learning this. Okay, this is, let's say this is our CMOS. Maybe CMOS schematic view of the maybe not gate. Okay, not gate. This is VDD, and this is VSS. Maybe this is Q. What I'm saying here is output should not be tied. Okay, this is a input A and this is output. Let's say if you if you connect this to ground, what it will do, like whatever the input you give, if you give the input here like let's say 0, then this will be shorted, but still the output is 0. Okay, even if you this shorted also, still the output is 0. And if it is 1, the input is 1 here, and this will be shorted, but still the output is 0. So whatever the irrespective of any input, the output gets 0. So this will cause the functionality failures. This is very dangerous to the design. So that is the reason you should not have the like output should not be tied to the ground. Okay, let's say you have one buffer here, maybe inverter. Let's say this is the inverter, right? The schematic view. Okay, if you tied this to ground, right? So yeah, every time it's zero only. What you give any input. So if let's say you're supposed to get the output is one. Okay, you give this output one to some other cell, maybe some AND gate. Okay, so you're supposed to get the input as one, but what you are giving here is zero. So the functionality is changing. Okay, the output it's supposed to come as high. Okay, but maybe the output is coming like hello. It's wrong, right? You're supposed to get high, but you're getting hello. It's wrong. That's the reason the output shouldn't be tied to the ground. It's an important point, guys. And also the next is no floating inputs. If you want, you can note down these points. It's a very important. Okay, no floating inputs. Okay, let's say this is if we consider the same cell. If this maybe this is the input, right? Maybe this is A, and this is B. So this input pin is not connecting to any other cell. Maybe something, maybe some, let's say some mux is there. Okay, some mux like this, 2 by 1 mux like this. And if it is not connected like this, any other cell, not only mux, any you name it, any cell, and that drives this inverter, and it should connect it. It should know if you are not connecting this, maybe some due to some RTL mistakes, they forgot to add the connection to this cell, then it will lead to some glitches. Okay, glitch is nothing but it's an undesired transition that occurs before intent value in the digital circuits. Let's say you get you're supposed to get maybe one here, but because of the glitch. Okay, I'll explain that topic in maybe in the crosstalk or signal integrity. But just understand, like, if you have the input floating inputs, you will see the glitches. So glitches also can cause the functionality failures. So maybe you're supposed to get some zero or one, but you like maybe okay, you're supposed to get zero here, but you are getting one. So that is the functionality failure. So we can write here maybe here the functionality failure here. Okay. Functionality failure. Okay, also this will cause the glitches. And also the chances of dynamic power consumption will be increased. Okay, will be increased. Okay, so like a dynamic power, like nothing, like just switching only, like nothing connected. Every time just switching, and because of switching, it will the power consumption will be more here, the dynamic power consumption. And also, and very important, it will go into the meta stability stage. Meta stability. At least you should highlight these points. Okay, if an interviewer asks you, you should tell if you have the floating inputs, the cell will go into the meta stability stage. Meta stability stage is like unknown input, so it doesn't know what it is. It doesn't know what kind of input it will get, right? So is this clear? Okay, so next, the multi-driven, no multi-driven. Okay, no multi-driven or driver, no multi-driver nets. Okay, let's see what it is. Okay, let's say you have one inverter and it is going, and one more inverter. Okay, it is connecting to one buffer. Let's say, okay, it is connecting to one buffer like this. Maybe this is A, B, and this is maybe C. Okay, let's say if you give the input as 0, you are giving input 0 here, and you are getting 1. And if you give the input as 1 here, you get 0 here. It's an inverter, right? So it will inverse the logic. So this pin, this buffer, like it will be in like a confusion mode, like what input it should take. It is getting two inputs, right? So it doesn't know like what input is the correct input to this buffer. So that is, this is the multi driven nets. So two nets are driving this uh, buffer. So guys, I think I should tell what is the driver and receiver also here. So the cell which driving the another cell is the driver. Here, let me, okay. Here in this case, these are the drivers. We call it drivers. Okay, remember this driver, because these two cells are driving some other cell. This is the receiver. Okay. Okay, this is the receiver, and then this is the driver. If I when I'm talking like driver and receiver, right, you should assume like this. Okay, the driver is like, okay, it is driving that cell, and receiver is like, this is driven by some other cells like this. We call in our entire like in our like in our in entire our job, right, we will in real time we will say like this only. Everyone, like if someone say you like your driver is not good, then you should understand, okay, my driver is driving some other cells. So maybe it's not good means like maybe it's low drive strength cells, or maybe some reasons. Okay, some reasons it is not good, we need to check that. Maybe your, if someone says like your receiver is not like maybe your receiver is driving by some other cells, means you should understand, oh, this is my receiver and it is driving by some different cell. Okay, you should understand like this. Okay, so this is the multi-driven nets. So you shouldn't have this kind of logic in your design. So where you catch them in the netlist checker. Okay. Then one more point is like no combinational feedback. No combinational feedback. Let's see what does it mean. Okay. So let's say you have an XNOR gate like this. Okay. Okay. And you have maybe two inputs, one output. Maybe this output is connected back to this input, feedback to this, again say this input. Okay, let's say you give the logic one here. Maybe this is A, the output is B. Okay, so this is X naught. Okay, so you pass the logic A. So the B becomes like let's say it will okay, you pass one and become 0, and again it will give it back here, right? Again 1, it will become 1 and 0. It's a never ending story. It's a feedback loop. Whatever, like it like whatever the output it will get, right, it will again passing back to this as a input to this again. So this is the combinational feedback loops. So you shouldn't see these kinds of logic in your netlist. Okay, like it's a toggling, like it always toggling 0 to 1, 1 to 0 like this. So it will also cause in like we in STA also the timing when you are calculating timing also, it will cause a lot of problems. So that's the reason, like you shouldn't have these kinds of logic in your design. Okay, so this is the uh, netlist checker. Okay, we learned like netlist should not have the output shouldn't tie to the ground, and no floating inputs, and no multi-driven nets, and the no combinational feedback loops. Okay, they shouldn't be present in our netlist. Okay, all good, but how do we check, right? So this is, there will be a command called check design dash netlist. Again, check design dash netlist. So this command will dump all the information of this. Okay, you need, it will dump the one report. You need to go inside that report and check if you have any floating inputs are there, the cell inputs it's floating, the output is tied to zero, I mean, ground, and any multi-driven nets or any combinational loops are there in that report or not. If you have it right, you need to immediately feedback to your full chip, or maybe the RTL. If you are the full chip owner, then you need to feedback to the RTL. Otherwise, if you are just a block level, like if you are block level engineer, then you need to feedback to your full chip guy, saying like the netlist you provided having these kind of issues, and please correct them and release one more net list.
It is a check underscore design,
Uh-huh.
then underscore netlist, or it is our command.
The command will be same actually. It's a check design. This is actually Innova's command. So maybe the Synapses command will be check underscore design. So basically in real time, right? There will be a flow like import design, yeah, and so floor plan, placement, CTS, and routing. So import design itself, it will check all this. So your job is, you need to, once the import design is completed, you need to get the reports from that stage. Okay, then you need to
Okay.
understand this. So if you like you don't need to perform these commands individually, like you don't need to open the ICC2 shell and perform this in real time. I'm telling you. Okay, for learning purpose, I think you should do it, because you don't run the flow here. There will be a nlib, will be the like already built-in nlib, we will be given, and we need to analyze the TP. Okay, you will not be run the flow here.
Okay,
So,
sir.
but in real time, because real time, uh, they will give you the inputs and ask you to converge the design, right? Here, for learning purpose, we are the students and we want to learn. So they just give you the end, the final end, maybe let's say the routed design. They will give it to us, and in that you need to check all this. Mostly in our design, everything will be clean only, because let's see, I don't know, even I will see with you guys that we will see whether we have these issues or not in the next coming classes. Okay, so yeah, but if you still want to check, right, these are the commands. Check design, you will like a dash netlist, maybe check design. You will also have this maybe, yeah, physical library and logical library, and all these kind of options will be available for this command. This command is nothing but like, let's say you written a proc, I hope you guys already know the basic tickle, right? If not, I'll teach you, don't worry. Let's say there will be a proc like this. You will define it, and there will be a add. You want to add some two numbers, and you will set here, like set A, set B, then maybe set C equal to A plus B, and you will close it. So this is the proc actually in the tickle. If you see, if you know, right, this is the proc. So this proc name is add. So what you will do, output will be like, you will add 2 space 3, then what it print, 5. So if you give like this, you will get this output. But this background, right? The background, in the background, this add proc has this much of like lines of code. So in the background, it will execute and give you this file, and it's the same like this. This is maybe Innovus, those guys written this. Uh, they have written a proc where it check these details, and also they will keep available of these app options. I mean, it's not app options, sorry, these are just options. So like netlist dash netlist, like this. Maybe here also we can put like maybe some options, like maybe like this. You want to subtract, addition, multiplication, like this, and you need to put dash subtraction, like this. Okay, then it will subtract and give you -1. And if you want to add it, you will put what, add, addition, others. Okay, it will add, it will give you the output like this. So it's the same concept, guys, like nothing, not a rocket science, just the same concept. It is they will define some procs. If you are very interested, maybe we can check this. I don't know if it will be available or not, we'll see. But in the real time, everything will be available, like even you can check the what is the code of this. But it's your purely your interest, like if you have the time you can check. Mostly you don't have the time, you will not be given that much of time. Okay, you will be struggling with your issues only. Okay, so yeah, we learn the library check and the netlist check and the timing check, or the SDC, I should say SDC, sorry, SDC check. Okay. Let's see, SDC. Okay, so SDC, basically, we need to check IO delays are properly defined or not. Okay, IO delays. I think I mentioned couple of times like IO delays, so that we need to check IO delays are properly defined or not. If not, then you like your timing will not be met. If not, then timing won't be met. Okay. So that's why you should make sure all your IO delays should be proper. Let me explain one more time again. Okay, let's say this is your block. Maybe let's say this is your full chip. Like they partition like this. Okay, and you have been given this ports information. Let's say one AND gate is driving through this port to some buffer or something, whatever. So some logic, maybe X naught, let's say this X naught, some logic here. But what the full chip guy, this is the full chip, okay? Full chip at top level, at chip top, full chip at top level, at chip top, and we can call anything. So when they do some by partitioning here, they need to divide this logic also, like in this partition, what kind of logic they should give it to you. So okay, they cut here, so the net is also getting cut right here. So what they will do, they will define a port here, the port. Okay, so let's say this is going to some flop. Okay, and maybe this input is going to some flop here. So they will have the timing, right? So let's say you have a time period like 500 ps. You will be given 500 ps of time period. So you need to fix the time in this. I mean, your data should reach, your data should launch and capture within this 500 ps. Okay, let's say this partition, like maybe this is A. Okay, so this is A and B, C, T. Okay, the guy B, so he may used 400 PS. Let's say, just let assume 400 PS. The B guy used. You how much you left? How much left for you? Just 100 PS. Okay, 100 PS only. But you maybe the data path in this block maybe huge, maybe like lot of logic been added, like and nor XOR and buffers, inverters. Lot of gates are added in your blocker partition. It is almost taking another 400 ps. You can't meet. You're not able to like your data path delay like 400 ps, 400, 800 ps total. 800 ps you are taking, but you have been given only 500 ps. The delta is 300 ps. Here your timing path will fail by 300 ps, right? So you don't know, like the B guy, you don't know that he already used 400 ps. He did not give any information to you, and you thought like you have a free hand and you can and optimize your path however you want. Okay, so then you are end up with the violation at the final. So to avoid this kind of confusion, what they will do, they will give the input and output delays here on each port. Okay, on each port, input and output delays. So that will be defined in the SDC. I think we already learned in the SDC inputs, SDC, right? There is a one point like in IO, like input and output delays it contains. We learned it actually. So that information should be given in the SDC. So in the SDC check, in the Sanity SDC check, it also checks whether the all IO delays are properly defined or not. If not, your timing won't be met. Okay. Next, the no unconstrained endpoints. Okay. Endpoints. Okay. No unconstrained. Should be no. Okay. No unconstrained endpoints. Let's see. In our design, everything should be constrained. Okay. Let's say this is your block, and you have the flops here and here. These are all your flops, and there will be a clock port here. Okay, so the clock should be distributed to all the flops in the design. It must. If the clock is not distributed, then how do you fix the timing? You don't know, right? Like it. What is the timing? We already learned, right? The two flops will be there, and the clock. This is the clock, and this is the data path. This is the flip flop one, flip flop two. This is Q, D pin, and C, maybe a clock. This is the clock pin. This is the D pin, Q pin, and the clock pin. So what here saying? No unconstrained endpoints means to check the timing of this path. So this clock pin should be constrained. This clock pins. That is what I'm saying here. So in this design, let's say these are the two flops I drawn here. So this has some logic. So these two, if it is not like clocked, then how you check this capture clock path, clock delay? You don't know, right? So your timing will not be the accurate. You will see some random timing, and it won't meet any time. So that's why make sure the moment you get the inputs, right, you need to check the health of the SDC. No unconstrained endpoints. If you have it, then it leads to some uh, wrong timing. Okay. Okay. Next, same all flip flops should be clocking. Same concept. Like all these sorry, all these flip flops should be clocking. So basically these kind of checks does in the SDC. Okay, let's recap one more time. Very important. Your basics, your fundamentals should be very strong. That's why I'm repeating again. So sanity checks is like to ensure the correctness or quality of the inputs. Okay. So basically we do only three types of sanity checks. One is library check, netlist check, and SDC checks. In the library check, there are two types of checks, like logical libraries and the physical library checks. Logical library, it contains the timing, power, and noise. Okay. Physical library contains the real layout topology of the cells. I explained here, right? What is the logic and the physical. So it will check these information. If it is missing, let's say some cell missing the footprint or the topology of the cell, then you need to feedback immediately. Okay, feedback is very important. You know it, and if you're not telling to anyone, you keep quiet, and no, I don't want to tell anyone. If you do like that, right, it's you will screw up your design. So you should immediately feedback to someone, maybe your higher like manager or someone. Okay, Then yeah, these are the commands to check the library. Check library or check design. Check design, like will have the options like this, physical library and a logical library. If interviewer asks you, you should able to tell this, at least this command, check design or check library commands will be available. We check the sanity checks through that command and we will analyze the reports. Okay, then netlist checker. So netlist check is like we need to check output shouldn't be tied to the ground of any cell. Okay, and no floating inputs. Floating, maybe interviewer, if you say like cross questions also you may get from the interviewer, like okay, you say no floating inputs, he will ask why. Well, like, okay, let's say I have the floating inputs in my design. What it costs, like what it will impact my how it will impact my design. So these kind of cross questions also interviewer may raise, so you should be ready with that. Like if we have the floating inputs, our functionality will be fail, and also it will cause the glitches, and dynamic power consumption will be increased. And main point, it will go into the cell will go into the meta stability stage. So that is the reason we should not have these no floating inputs. Okay, then no multi-driven nets. If we have the multi-driven nets, the input pin of the cell doesn't know what inputs they should pick. That's the reason. Maybe if it is interview face to face, right, he may ask you to draw the one example. He may ask you like, hey, draw one example for this multi-driven nets. So you need to draw like this. Okay. So you guys are freshers, right? So they will ask on they mostly stress on the basics only. They don't want you to be like expert in uh, the PD flow. So basic knowledge they need. Okay, and the no combinational feedback. They may ask you like also what is this combination feedback, and you need to draw this kind of picture, and you need to explain like this. Okay, then SDC checker. SDC is like it checks the all IO delays are properly defined or not. If not, then timing won't be met. We should make sure all the IO delay should be defined properly in the SDC file. SDC file is one of the input, right? These are all one of the inputs only. If you remember, library, netlist, and SDC. Okay, and no unconstrained endpoints. So all the endpoints, nothing but the flops only. Endpoints and start points. I told you, right? In our STA class, I told you like each start point is also be an endpoint. Okay, each endpoint is also be a start point. So here they mention like endpoint, but here we say it is endpoint, but the endpoint is nothing but the flopper. So you should understand all flops should be constrained, and also uh, the flip flop should be clocked. All flip flop should be clocked. So I hope you understand this sanity checks today.
Yes, sir.
Good. If you have any doubts, we'll discuss. If not, I think we'll see this whether we covered all or not. Think this is the netlist check. I'll give you this document. You can go through it. If you don't understand, you can come back to me and we can discuss more. Okay. Uh, I think we covered the netlist check and timing check, or else the HDC check also. Yeah. This also we call as HDC check also. And library check also we covered. Okay, I think this is enough for today. You guys please read these three slides, and by head, I'm telling you, by head, this literally by head them what it contains, and the inputs and the sanity checks. Why do we do the sanity checks? Okay, literally you by head them. Then to the next class, we will discuss on the floor plan. This is the okay. I think let's cover this also. Then you have some time, right? It's okay. I'll take another.
Yeah, okay, sir.
Okay. Okay, so we discussed the inputs and the sanity checks. Okay, let's get into the actual flow. So we already know like our physical design starts with the floor plan. Okay, the floor plan and the placement and the CTS means clock tree synthesis and the routing. Okay, this is the actual flow, the basic physical design flow. Okay, the partitioning is like we already know it's a breaks the whole chip into the sub chips, and this will be given to all our engineers. And the floor plan is like so we will there will be some modules, and that module placement will be happen, and also macro placement. Okay, this is very big topic, and we cover this later. And the power planning is like there will be some uh, like like we will be given some template, a power template, like what type of power your block should get. Basically this you will have if it is a one power domain, right, like you will see one power like VDD, let's say VDD, and ground is always a ground VSS or ground. So if it is a one power domain, if it is, if let's say your block is a low power design, okay, you will see many powers like this VDD 1 2 and many. It depends like what kind of logic you have in the design. Okay, and the placement is nothing but like it just plays the standard cells in the design. Okay, and this is the CTS, it just build the clock tree. And routing, we all know that it just give the physical connection to all the cells on of the nets. And timing closure. Okay, this is the physical design flow. Okay, let's see this. Okay, this is the decision of the physical design flow. Like let's say you okay, floor plan you have done and it is good, you verified it is good, and the placement you are done, it is also good. Okay, then CTS, this is bad. Like what we see, how we conclude like whether the CTS is good or bad, like we check the timing of the each stage. We will check the timing and congestion, both timing and congestion for each stage. Okay, CTS, let's say here timing and congestion is bad, then what you will do, you need to make some decisions. So the like you need to go back to the your standard cell what standard cell placement, or you need to arrange them again floor plan. So these kind of decision, let's see. Yeah, okay, so you have been given there is a full chip. Okay, so there is a full chip. Okay, and actually is my marker is visible to all of you? No?
Yes, sir.
Yes, sir.
Okay, good. Okay, so you have done, okay, there is a full chip, and they did some partitioning, and this is your partitioning. And next the step is you will do the floor planning. The next immediate step is the floor planning and the placement. The combined here both floor planning and the placement. If it is good, it check, I told you, right, it is everything we decide based on the timing and congestion. Okay, so is timing and the size is okay? If yes, it will go to routing. Okay, if yes, it is a timing and size means the congestion, everything is fine, it will go to the routing. Okay, then the routing is completed. If it is yes, it will go to all the way till here. Compaction nothing but some extraction only. It's nothing but like we are the sign off checks only, what we check LBS, the timing, everything, na? So that is what. And it will go here, it is timing like maybe LVS, everything is clean, right? It will go to the extraction and verification. Okay, here the STA. Okay, STA, here is the sign off tool. STA means the prime time. Okay, PT shell. Okay, so in your like the timing, you see it is met. Okay, in the ICC2 shell, but this is just the tool where you implement your PNR, place and route execution. Okay, but this is not the sign off. Okay, ICC2 is not the sign off, guys. Sign off tools are different. Where that does the checks very all the results accurately. And if this sign off tool says good, then only you will exit the partition. Otherwise, you will be again still doing it. Okay, here STA is PT. If it is saying yes means okay, it will go to the fabrication. Okay, fabrication means like where the your block or your chip being printed on the silicon wafer. So that is the fabrication. Let's say your the STA is saying your timing is not meeting. So it will come here. Okay, and we will check can be fixed by rerouting. We will go here. We'll open our routing database, the final DB, and we will see the path, which paths are not meeting. Okay, the paths, let's say that path is routed very badly, like lower metal layers, like maybe M1, M3. Those are the very lower metal layers. Lower metal layers will give the high delays, the RC delays, okay, resistance and capacitance. That is the net is nothing but the resistance and capacitance, the combination of resistance and capacitance. So the RC delay is high. So we will try to route them in the top metal layers, like maybe M14, M15, which has the less delays. Okay, because the width will be more, right? We have seen in the dot left file the width of the metals, it's changing actually. So we use that big premium metal layers, and if it is fixed, good. Then you will go to this step again. You will specs you will dump. Okay, specs, guys. You understand this spef? Steps are the extraction. It will contain the extraction details, like your net. Let's say you have one buffer here and one buffer connected here. So this net will, the spef tool or the extraction tool, what it does, it will break this net and convert this into a resistance and capacitance, and it will calculate the delay values. That is the extraction tool does. So this we call as a spef. Okay, so it will generate the specs, and it will give the specs to the STA. Okay, STA will check that same path timing. If it is meet, okay, you're good. If it is not meet, again it will come to here again. Okay, now what you decide now? Okay, routing is not fixing. Let's check whether this can be fixed by this violation can be fixed by refloor planning. Okay, if it is yes, okay, if it is yes, then you will come here and you will arrange your macro placement and the module placement, everything here. Then again you will go to here. You will check the timing there again. If you feel that timing is good, then it will go to the routing, and again they generate the steps, go to the STA, they check the timing. If it is good, okay, this is I mean, you're done with that. Again, see, if it is not meeting that path, again it is not meeting, right? It happens to be honest, it happens in our real time projects. So again, it's a kind of iterations, like you need to trial and errors, you need to make a lot of trial and errors. So you should not get pitched up with this process. So again, you need to go back to this stage, and okay, now, okay, you decided routing is not fixing. Now you decided, okay, floor planning is also not fixing. Then you need to go the partitioning itself, like maybe if they give the partition like very weird shape like this, maybe the weird shape if they give, maybe this time what they will do, they maybe give some square shape. This also affects the timing. Okay, it affects the timing actually. If they give this square shape, right, you will have the good routing resources. Okay, like this. So yeah, I don't think so. You will go till this stage. Mostly, you will be fixed to the paths at either routing or refloor planning. Mostly in these two stages only, you will fix the timings. So yeah, if it is all good, then you tape in or tape out the partition, and you are done. So I hope you understand. This is the like a decision making, like what you at what time what you need to do. This is just flow. Okay. I hope you understand this. You have any doubts?
Yes.
No, sir.
Okay. I'll give a pause here. I think this is good enough for today. I'll give a pause for any questions if any one of you having. Ranjita, you have any doubts?
No, sir.
Good. Samir,
No, sir.
Vijay,
Mm,
okay. Uh, Subhani,
No, sir.
okay. Syed,
No, sir.
okay. So I hope you guys understand very well. Tomorrow I'll ask some basic questions again. So don't get afraid of these basic questions. Okay. I just want to make our sessions very friendly and very interactively. That's the reason I'm asking the questions. Otherwise, I don't have any other intention. Okay. So you want to learn something, right? So you're spending and investing time here. So at least you should learn something. So if someone asks you like, what is the input, you should able to tell minimum. Like you should talk about at least 1 minute about the inputs and sanity checks. If anyone asks you sanity checks, you should tell what kind of sanity checks and why do you do that checks. And yeah, so what is the physical design flow and what involves in that flow? At least you should tell like, okay, we start with the physical design flow with the floor plan. Then we will give that to the placement. Then it will go to this clock tree synthesis or CTS, and the final stage is the routing. So at least you should tell like this. Okay, tomorrow, I mean the next, maybe I'll let you know, guys. Tomorrow, yeah, I think we covered almost. This is just an import design. This is nothing but just same import design. I told you, right? Import design, just check all the sanity checks, like unifying the netlist. Like if any empty modules are there, module nothing but it's a logic. Like empty module mean, like I shown you like the netlist, right? How the netlist look like. It will they will define with the module. The command starts with the module. If inside that module, if it doesn't have any logic, it's a useless, right? Why should we need that? So that kind of issues it will solve in the import design. I mean, it will check actually, not solve. It will check and we need to verify and feedback to the full chip. Okay. So this is the same thing, import design. Yeah, I think we covered all this. Maybe